In the first part of this video lecture, we saw the first Borel Cantelli lemma, and we discussed a lot the motivation why we would care about a lemma that allows us to show that a sequence of events will have probability 0 to occur infinitely often. And we saw the proof of the lemma, and now we're going to see the converse of that lemma. That will be Borel Cantelli lemma 2. It is not exactly the converse, it's quite different in spirit, because now here we really need the sequence of events to be independent. So these events are assumed to be independent here, and in Borel Cantelli lemma 1 there is no assumption of independence. So it is the converse in the sense, if the sum of these probabilities is infinite, then the probability that these events occur infinitely often is 1. And this is good because sometimes we want to show that some sequence of Borel functions or some sequence of random variables does not converge. And one way to show that it does not converge is to show that, well, it would have to be 0 if we wanted them to converge by the proposition of the previous video lecture. And if we can show that it's not 0, one way to show that it's not 0 is to show that it's actually 1. So this can be very useful. The proof of Borel Cantelli lemma 2 is a little bit more involved, even though the idea is basically the same idea. So we want to show that the probability that an occurs infinitely often is 0, which means we want to show it is 1, which means the probability of its complement is 0. So this is what we want to show, that it's 0. But now, what is this event? The complement of an occurs infinitely often. Well, we have seen already, this is the same as an complement occurring eventually. This is by De Morgan's laws, eventually. Okay, and this will be the union over n of the intersection over m of the complement of am. But just like in the previous proof, but now the opposite, we can use continuity, but now this will be continuity from below, because this bracket here in red, this is non-increasing in n. As we make n larger and larger, we are taking an intersection over a smaller family of sets, which means this set is increasing. If we call this set here Bn, then Bn is non-decreasing. And if we take the union of a non-decreasing sequence, well, we have this property. This will be here continuity from below. So we can compute the probability of this union by a limit. But now we can consider the following. If instead of going up to infinity here, we take this intersection only up to some number k, okay, we can write this as the intersection over m going from n to infinity of some, I used b already, this would be ck, cnk, if we go until k. This will be the intersection over k of ck, if k going from n to infinity, if we denote ck as ck to be the intersection when m goes from n to infinity, not infinity, k of am complement. Okay? So instead of asking all these am complements to occur, we're going to ask only these ones. So finitely many only. And so we can take the limit over k by continuity from above. We are in a probability space now, unlike Borel Cantelli lemma 1. Borel Cantelli lemma 2 only makes sense for probability spaces because you're talking about independence, and now you're talking about intersection of events, and we are just about to use the property of independence. And the whole point was to make this k here finite. And why do we want this k to be finite? Because now we're taking the intersection of finitely many events which are independent. So this will be just the product of the probability of these events. And we know what's the probability of AM complement. This is 1 minus the probability of AM. This is what is written here. And now we're going to make an estimate from above of this product, and we're going to use something a very common estimate to make, which is 1 minus x is less than e to the minus x for x larger than or equal to 0. You can see this here in the graph of the function. This will be e to the minus x, and this will be 1 minus x. So I'm just now replacing 1 minus this probability. I'm making an upper bound for an exponential. Why do we want to do that? Well, because we have a product, and products, they play well with exponentials. Because what is the product of this exponential here? Well, the product of exponentials is the exponential of the sums. So this equal here just means we're taking, instead of multiplying all these exponentials, we're taking the exponential and we're summing the exponents. And of course, as it always happens, we just transformed the problem once and again until we start to see here what's in the statement. Let's go back. What's in the statement of Borel Cantelli lemma 2? That this series is infinite. And that's what we're writing here. This is just a partial sum of a diverging series. So as now k tends to infinity, this will tend to minus infinity. And as such, it will tend to e to the minus infinity, and that is 0 for every n. This is 0 for every n, and then taking the limit over n doesn't change anything. We're still with 0. So we just show that this probability actually is 0 because it's equal to something, which is equal to something, which is equal, until it is less than something, which again continues to be equal, and equals 0. So if a probability is less than or equal, or probability is less than or equal to 0, then it is 0.